the second part of chapter 12, the linear kinetics of human movement. So in the lecture, I'm going to be showing you a couple of new formulas that we're going to be used and the quantities to study human motion, the biomechanics, the kinetics of human motion. So the first thing, we have a quantity called the coefficient of restitution. That's E. The coefficient of restitution, E, it's a unitless number between 0 and 1 and serves as an index of elasticity for colliding bodies. This coefficient is a measure of how elastic or plastic the collision is. And we're going to learn how to calculate it in two different ways. First one, using velocities, and the second one is through using height, dropping an object on a floor of different materials. And that's important in biomechanics, especially in sports, in athletics. Now, the closer E is to 1, the more elastic the impact, which means impact is elastic. So if I say between 0.5 and 0.6, which one is more elastic? 0.6. The closer to 0, the more plastic the impact is. The closer to 0, the more plastic the impact is for the collision. So that is the definition of it. And then, so what does the coefficient of restitution describe? When two bodies undergo a direct collision, the difference in their velocity immediately after impact is proportional to the difference in their velocity immediately before impact. So it's about the velocities before and after, the differences between them. So we are saying that this coefficient of restitution is saying that if you have two objects colliding, the velocity before the impact and the velocity after the impact, they're proportional. And that proportionality factor is our coefficient of restitution. This is the formula. It's measured as minus E equals the relative velocity after impact divided by the relative velocity before impact. So you will see that V1 minus V2, so V's are the velocities after the impact, U's are the velocities before the impact. So the difference between the velocity after the impact divided by the difference of velocities before the impact equals to minus E, which is the coefficient of restitution. Now, if you look at the schematic here, you can see that we have two balls. They're colliding. U's are the velocities before. So U1 is the velocity of the left ball going to the right, and U2 to the left. And make sure that this is velocity, which means that we have to have vectors, right? One of them should be positive and the other should be negative. And then you have the velocities after the impact, V1 and V2. So V1 minus V2 equals minus U1 minus U2. And that's how you measure E, which is the coefficient of restitution. Now, in the exam, if I'm asking you to report E, you don't need to report minus E. You need to have the absolute value of it, or the negative of that value, to get you the value of E. And the difference between the differences in two balls velocities before impact is proportional to the differences in their velocities after impact, and the factor of proportionality is actually the coefficient of restitution. Now, this is the first way in which we measure this coefficient. And now the application of it, actually, most of the time it's in sports and in practices, and we measure this coefficient in a different way. We measure it using the height of dropping a ball on a surface. So I can say, well, I would like to find the coefficient of restitution of this floor compared to the coefficient of restitution of the floor outside where we have the carpet. So each floor has different coefficient of restitution. So how would you do this? We have this so this is the first formula, which is the velocities. The second formula is what is the relationship among the impact velocity, temperature, and the coefficient of restitution. So we'd like to study the effect of other parameters on this coefficient of restitution. So we can say that, well, increase in impact velocity and temperature increases the coefficient of restitution. So if you are in a warmer place, this coefficient will be larger. And if the impact is faster, this coefficient also larger, will give you a larger value. So to measure it in height, so this is E equals the square root of the height of the bounce divided by the height of the drop. So let's say I have a ball here and I'm going to drop it. This height, this is the height of the drop. When it bounces back, that's the height of the bounce. The ratio between the two, take the square root. That is also another way to calculate the coefficient of restitution. So E is the coefficient of restitution. So we can measure it using velocities. We can measure it using height, and the velocity and temperature affect this value that we're measuring, these two. Any questions so far? We good with this? Right. H drop is the height from which the ball is dropped, and HB is the height to which the ball bounces. The ratio between the two under the square root is actually the coefficient of restitution. This is an example. So you can look here. If you are bouncing different balls on concrete or on wood, you will have different bouncing height. So you can see that for a basketball, bouncing on wood is higher actually than bouncing on concrete, as opposed to all the other different balls. And that's something to do with the material of the ball itself. So the coefficient of restitution will be different in each one of those values. So the bounce height of basketball, golf, racquetball, and baseball all dropped onto the same surface from height of 1 meter. You will see each one of them has different values. So the baseball in concrete goes higher, right? Which means it's more elastic on concrete than on wood. Now, this is important for people who do design for sports and arenas, that you need to do these tests frequently. And the other thing is that the wood and concrete, because of continuous use, it changes its property. So these tests need to be done continuously. Okay, note that the basketball bounces higher on the wood floor, but the other ball bounces higher on the concrete. So they have more elastic collision on concrete, except the basketball has more elastic collision on wood. So this is a quantity you've probably never seen before. Now, I would like to go into quantities that we know of, but we would like to use them in biomechanics applications. So the first one, mechanical work. How would you define work? Force times distance. That's work. That's mechanical work. So it's the product of the force applied against resistance and the displacement of the resistance. Now, this is displacement. It's not the distance itself. So if you have a pendulum, the displacement is between initial and final location, but the distance itself is how much that pendulum is traveling. Remember this, when we said, well, if I have this pendulum and it went up there and then went down there and then came here, the displacement is just this, right? But the distance is the entire length of the path, that it took. So we would like to multiply force with displacement, not distance. W equals force multiplied by d. And the unit of the work is actually Newton meters, but we are calling it joules. So Newton meters is joules. Now, so that's mechanical work, force multiplied distance. What is mechanical power? So it is the rate of change of work with respect to time. Now, the rate of work production, with respect to time, and calculated as the work divided by the time during which the work was done, and that's the formula. So P equal W divided by T, delta T. W is force multiplied by distance. You can rewrite the power as force multiplied by velocity. So it's either force multiplied by velocity or work divided by time, the rate of change of work. We know about these, but we would like to now try to use them in biomechanics, questions and applications. The unit of power is watt, and watt is joule per second. So that's the power. Now energy, remember we have potential energy and kinetic energy. So the potential energy is mgh, the mass multiplied by the gravitational force, acceleration multiplied by the height, and the kinetic energy is half mv square, right? Half multiplied by mass multiplied by velocity square. So the mechanical energy is the capacity to do mechanical work, and its unit of energy is joules, and it's J. That's how it's denoted. And there are two forms: kinetic energy, potential energy, and we're going to solve together a couple of questions looking at how can we use these two quantities in biomechanics applications. Now, kinetic energy, half mv squared, right? Potential energy, it's weight multiplied by h, by the height, and weight is actually mass times gravitational acceleration, mg, h. So those energies we know: potential energy, kinetic energy. I would like to introduce a new type of energy called strain energy, because that's an important aspect in biological tissue as well. It's very important for biological tissue. Here's the thing. Do you recall that I probably told this to you a couple of times before, that we don't care about a biological system when it's doing its function. What is important most of the time in biological application of how quickly it recovers. So if you're deforming skin, you care about how quickly it goes back to its normal structure. So this is called strain energy, and that's the strain energy is the capacity to do work by virtue of a deformed body returned to its original shape. Now, this is different from, so in the skin was an example that's not going to help us here, but the point is that you are storing energy in a deformed body, and then you want to reuse this energy. Okay, so remember, deforming a body, but then reusing the energy that was stored in the deformation for mechanical work. Something like that's useful for us. We have formulas. So U is the strain energy, and it is half the velocity multiplied by sigma, which is the stress, and epsilon is the strain. So if you multiplied all of them together, you will get something called the strain energy, right? Or half V E epsilon square. Now E is the elastic modulus, which is the, remember the elastic modulus is the slope of the stress-strain curve, right? Right. So that is your stress, this is your strain, the slope of it is the Young's modulus or the elastic modulus. That's how we call it. So if you multiply those, half V divided by E by the stress square or the strain, you get something called the strain energy. So now we have three types of strains. Oh, actually we have energies. So far, we have strain energy, kinetic energy, we have potential energy. This is the example. Yep. During a pole vault, the bent pole stores strain energy for subsequent releases as kinetic energy and heat. Now, when we talk about heat here, we need to introduce thermal energy. So you have kinetic energy, potential energy, thermal energy, and the strain energy. So let's say I'm trying to throw a ball up in the air, and the only acting acceleration is gravity, right? For the gravity, the kinetic, all the energies will be conserved in the system. So when gravity is the only acting external force, a body mechanical energy remains constant. So kinetic energy plus potential energy should equal to C, a constant value. C is constant. That is a number that remains constant throughout the period of time during which gravity is the only external force acting. And if you look at this example here, so if we are throwing a ball up in the air, to the left here, you're looking at the height and the potential energy. Now, what's the formula for potential energy? mg, right? Mass multiplied by the gravitational force multiplied by the height. So that's your potential energy. On the right hand, you have the velocities and kinetic energy. What's the kinetic energy? Half mv squared. Now, because only gravity is acting here, the summation of kinetic energy plus potential energy should always be constant. So the whole thing should be 29.4. If you add 24.5 to 4.9, you should end up with 29.4. Right? So if you're adding this number, that's the potential energy, plus this number, kinetic energy, they should add up to this, because Here I have 0 kinetic energy. Summation of them should be 29.4. Kinetic energy plus potential energy should always be the same. If you go down here, that's 19, add to it 9.8, they should give us also the 29.4. Now, what is the principle of work and energy together? So we have a principle that combines them together. What we are saying that the work over force is equal to the change in energy that is produced in the object acted on. So what happens that you will say that W, which is the work, remember it's force multiplied by distance. But if you would like to correlate work to energy, the work itself is the change of potential energy plus the change of kinetic energy plus the change of thermal energy. So if you add all of them together, you will end up with work. So this is the relationship between work and energy. So all of these concepts are things that we're going to be using and in biomechanics, and I would like to cover them.